So this talk is about gait basics and the terminology we use to describe gait and how gait speed matters to us clinically. The objectives are listed on Foxtail, but specifically here we're going to talk about these descriptors of gait, gait speed, and clinical application. So the first basic concept is that the trunk is a passenger and that the legs kind of are the motor that moves the passenger around. And to understand how smooth of a ride the trunk gets, be sure to watch the short video on Foxtail called Smooth Ride, Trunk Movement and Goals of Gait. A clinical framework for the goals of gait is balance, energy conservation, and forward progression. The importance of balance is reinforced by the ability of the person to assume a single leg, a standing position, and then maintain balance while moving. Energy conservation has to do with their ability to move forward without expending excessive energy so they can go the distances they need to perform their tasks. And then finally, efficiency, incorporates the idea of speed so they can get there rapidly in a way that's timely, so they can cross the street before the light turns red, basically. And so those are the kind of clinical framework that a lot of your courses will use. So when thinking about gait, the most basic measurements are spatiotemporal, meaning spatial has to do with distance. So, in essence, we would define a stride length as a distance measurement from the first initial contact to the second initial contact on the same limb, and that's what's illustrated here in two right heel strikes. And then a step length would be initial contact on one side to the initial contact on the opposite side. And then temporal variables would be timing of gait events and things like gait speed, which we'll talk about more in a minute. In this particular graph, we're going to go over every detail of it in class, so you're expected to have this completely memorized as early as you can, because basically this is how we talk about gait. In this particular slide, it's a reference slide for you, and you'll notice that there's some basic definitions here on the left, which are reinforced here, and then here's some kind of average values that'll be helpful to us as we go through the gait unit. And you'll want to come back to this slide and look up things like, note that stride length here, some average values are 1.3 to 1.6 meters. Step length about half that, which is what you would expect. You would also kind of look down here and find speed, and then speed of walking varies between 0.82 to 1.6 meters per second, with 1.3 meters per second being average. So this particular slide is a reference, or it's a glossary of terms for you to reference as we go through this unit. So now that we've got some introductory material, we'll be doing some exercises in class. So be sure to do your best to review the basic descriptors of gait in terms of periods, tasks, events, periods, tasks, and phases and cycles of gait. So let's talk about now the maturation of gait, or when gait becomes normal. So we're going to use speed to talk about when gait becomes normal. So first, it's important to recognize that speed is basically cadence times stride length. So the frequency of strides times the length of the stride. And so what we can see here is essentially the speed, or in centimeters per second. So 160 is 1.6 meters per second. And then age here on the x-axis. So you can notice essentially that there's a slight slope here until about 4 years of age, and then it kind of levels out with some variability in speed. So normal walking speed is usually considered about 3 miles per hour, and that means that it varies from 1 meter per second to 1.3 meters per second. And so we can see here at about 4 years old, children start to assume kind of an average walking speed, or the lower end of average, which then they'll increase slightly as they grow, because as we'll see in a minute, stride length continues to allow them some flexibility in the speed they choose to be their preferred walking speed. And then normal cadence would be 120 strides or steps per minute. Okay, so then if we look at cadence and stride length separately, how that gives us an insight of when people mature, we can look at those independently. And we can kind of see here is that essentially stride length continues to increase even past 7 years old. And so that shouldn't surprise us because a person's growing, so there's typically there's some additional stride length that becomes available to them as they get taller. But then if we look at cadence, it's interesting because it pretty much starts very high in a young child and then decreases and continues to kind of decrease, but it starts to plateau at around 6 or 7 years old. But you can see the variability is also quite high. And so the idea is that basically cadence tends to hit this 120 kind of level a little bit earlier than you would for a stride length, which is going to continue to increase. But people basically adjust their cadence to have an average kind of walking velocity of somewhere between 1.2, 1.0 to 1.3 meters per second. Okay, so let's shift now to some clinical application. So in this study here, they're looking at stride length and cadence as measured at free speed or preferred speed, and the fastest speed a child could walk. And in this case, they're looking at children that are healthy and then also children that have a diagnosis of some type of spastic diplegia or cerebral palsy type of problems. And so essentially, if we look at the graph here, this is the difference between their free or for preferred speed walking and then when they're asked to walk as fast as they can, that difference. And so we're looking at velocity, stride length, and cadence for that difference between free speed or preferred speed and then fast speed walking. So let's focus on the healthy children in white here. And so we notice that they improve their walking speed by 0.8 meters per second, and they do it by increasing their stride length by 0.3 meters and then increasing their cadence by 0.45 steps per minute divided by 100. And so essentially they're taking quite a few more steps per minute than they would have otherwise. And so basically it's a 37% increase in cadence and a 26% increase in stride length. So some balance of both stride length and cadence, as you might expect. But now if we look at the cerebral palsy children, or the children with some motor problems in their limbs, we can see here immediately that they can't increase speed as much, and then also that essentially their cadence is relatively similar. They're increasing here 0.39 versus 0.45, roughly similar. And then as compared to like their ability to increase stride length is quite limited, about significantly less than that of the healthy children. So immediately we understand that like stride length and cadence and speed all give us a variable that's real functional to patients, and also gives us some insight into whether it's kind of a motor control problem at a cadence level, or if it's kind of a local control problem at the joint level. So it's more about the locomotor engine that's being used for them to get or achieve speed. We see something similar here We look at adults, an adult problem, Parkinson's disease, and also a neurologic type of problem. And they did almost an identical experiment where they have these Parkinson's patients walking at free and fast speed. We also have young and age-matched controls, which are going to tend to be older because these patients are similar to the Parkinson's patients, which are older. So we can use this to kind of gain insights on, average walking speeds and how changing speed kind of is affected by step length and cadence. So essentially we can see here's our kind of expected increase from free to fast walking, and that the age-matched controls, can't get to the same increases in speed, and the Parkinson's patients have, much more marked lower speeds and aren't able to increase speed as much. It's kind of what we would expect. But then if we look at comparing step length and cadence, what we notice immediately at first is that, again, cadence is preserved, but step length is impaired, and that really goes in each particular group. So the step length is impaired, in essence, in the elderly as compared to the young, and then also significantly more in the Parkinson's patients compared to both the young and the elderly. And then we can also look down here at the percent change from free to fast, and that's what's represented here on the x-axis, and we see speed, step length, and cadence. We notice essentially that as a proportion of their starting speed, the Parkinson's patients are doing really well in terms of increasing speed, and that they actually do it by increasing both step length and cadence. So unlike the children with cerebral palsy, they're not having problems with kind of spasticity in their limbs. It's more of central drive from the cerebellum, and so the effect of this is more global than the kind of local problems that the kids with cerebral palsy are having. And so essentially here we can see that there's the strategy to get to this kind of fast speed for a Parkinson's patient involves both step length and cadence. And just one more look at the Parkinson's patients. This is the percentages correlated from the time from the disease, and you can see they're out like 20 years. That's what's on the x-axis now. And so the longer the time they have the disease, then the more they try to increase cadence. So cadence is the open circles, and that the longer they have the disease, the less they can increase stride length. So even though they're trying to increase it, they have a more difficult time. And so essentially this particular graph just kind of shows how gait speed and cadence and stride length can be used to kind of track progress in a patient group over time. So what are we learning? We're learning that gait speed, stride, cadence, and other spatiotemporal measures are potentially important for us to understand from a theoretical perspective how to intervene with patients, and then also as indicators of disease progression. They're important to patients. So we'll explore this more when we look at gait speed as a vital sign in an exercise in class. Thank you very much.